I'm Norman Wappeger. Today we're going to investigate more deeply this notion of reflections in universal hyperbolic geometry. We're going to connect reflections with perpendicularity and show that reflections in fact maintain perpendicularity of points and lines. And then we're going to introduce the interesting notions of midpoints and their dual notions called bisectors. So last time we introduced the idea that to a hyperbolic point we can associate a projective 2x2 matrix. And exactly here's the correspondence. The point x to y to z corresponds to the matrix with diagonal entries y and minus y, and off diagonal entries x minus z and x plus z. This is a trace zero matrix. The trace is the sum of the diagonal entries is necessarily zero. And this matrix came about by thinking about the action of the reflection in a point A. So if there's an arbitrary point A, then if we draw lines through A that meet the null circle, the 2 points that they meet at can be thought of as being reflected points in the point A. So we encoded that algebraically with this, there are actually 2 theorems, the reflection matrix theorem and the reflection matrix conjugation theorem. So I've put them together here. The first one says that if we have these 2 null points, alpha 1 and alpha 2, given by projective coordinates t1 to u1 and t2 to u2, remember that's how we parameterize the null circle, by a projective ratio like this. Then we have a situation like this where the 2 points determine a line passing through A, so A lies on alpha 1, alpha 2, precisely when this relation is satisfied by the 2 proportions. That one of the proportions is obtained from the other proportion by multiplying on the right by this matrix M sub A. And M sub A squared is equal to 1 typically, and so we can also rewrite this, put it on the other side as well if we like. And then the reflection matrix conjugation theorem says that when this happens, we also have this relation between the 3 matrices associated to these 3 points. Null points also have matrices associated to them, and so M alpha 2 equals MA times M alpha 1 times MA. So this is a matrix formulation of this collinearity of these 3 points. So a little exercise, show that this kind of combination, MA, MB, MA, that the trace of that always equals 0 for any points A and B. And so now let's define what we mean by the reflection of a general point in the point A. We know how to reflect a point on the null circle in A. Now we're going to use that same formula to extend this to a general point. So here's the official definition of reflection in the point A. We say that C is the reflection of B in the point A precisely when M sub C equals M sub A, M sub B, M sub A. And in this case, we write, this is our notation for it, C equals B sigma A. So this means that C is the reflection of B in A. Let's do an example. Suppose A is the point minus 3 to 1 to 1, and B is the point 0 to minus 4 to 5. Where would this be in our picture? Well, minus 3 to 1 to 1, since there's a 1 in this last column, that's really like the point minus 3, 1. 1, 2, 3, that's minus 3, 1. There's the point A. And B, 0, minus 4, 5. If we divide by 5, it's the point 0, minus 4/5. So 0 in the x direction, minus 4/5. There would be the point B. So let's try to reflect B in A using this formula. Well, we write down M sub A and M sub B and then M sub A. Here's M sub A, obtained from here by the y coordinate going down the diagonal and it's negative. Then x minus z right there, and x plus z right there. There's MA there and also there. And M sub B, well, minus 4, there's the y coordinate, and it's negative there. The difference, 0 minus 5, is down here, and the sum, 0 plus 5, is up here. Now we compute the product of those three matrices using the algebra of 2 by 2 matrices and matrix multiplication, and we end up with this matrix, 18 minus 9, 117 minus 18. And according to our definition, that's the matrix M sub C. So how do we recover C? Well, we sort of have to unravel this. The general formula is we take this thing here and multiply it by 2. That's going to be the middle term. And then this thing here plus this thing here, that's 108. It's appearing right there. And this minus this is minus 126. That's appearing there. And these numbers here have a common factor of 2, which we can divide out. We get minus 54, minus 18, 63. Where by convention I try to make the last element always positive. So that's the element C. That's the reflection of B in A. And where is this on the page? Well, to see where it is as a point in regular x and y coordinates, divide by the last coordinate. So we get minus 54 over 63. Oh, so that's almost minus 1. Divided by minus 18 over 63. Well, that's something like a third or a quarter. And so that's minus a third down that direction. So there's C right there. So the reflection in this point A sends B to C, and conversely it sends C to B. So this calculation is actually not too bad. It's very accessible to calculation, this kind of reflection in points. Let's do another example, which is quite different from the other one. The example this time is going to involve this point A, 4 to 3 to 5, which I hope you recognize as a null point. It's a null point because 4 squared plus 3 squared minus 5 squared is 0. It means it lies on the circle. In fact, it's somewhere there. And B, random point, 4 to minus 3 to 2, that's right about there. Let's find the reflection of B in the null point A, using exactly the same formula. So here's MA, you can check, here's M sub B, here's M sub A again. Multiply the three matrices, we get this thing here. Divide by a factor of 6, and we get 3, 9, minus 1, minus 3. And lo and behold, we see that it's exactly the same as M sub A. What does that mean? Well, it means that the reflection of B in A is A itself. This is not like a regular reflection. And it's because the point A is not like a regular point. It's a null point, it's a special point, it behaves differently from other points. Here's the general theorem that captures that. The null reflection theorem. If A is a null point, then the reflection of any point B in A is A for any point B. And I'm going to leave this proof as an exercise for you. And so it's an exercise to actually work out a proof. And a little hint, well, you're going to have to show that M sub A, M sub B times M sub A equals M sub A for any point MB if A is a null point. And I remind you that we know what the formula for M sub A is for A, a null point. We obtained that in the last video. Why are reflections so important for us? It's because reflections are going to be the isometries in hyperbolic geometry, or they're the generators at least of the isometries. And that means that they are going to preserve all the fundamental formulas in the subject. Any formula or any concept, if we apply a reflection to it, we're going to get different points and different lines which are going to obey the same relations. We're going to see that later on as we go. Right now we don't have any metrical notions. I have not introduced notions of quadrants and spread, which are the hyperbolic analogs of distance and angle. So we're not operating metrically yet. really all we have is the notion of perpendicularity. So I'm going to show you now that the perpendicularity notion is preserved under reflections. That's going to be a main fact. To do that, we have to connect perpendicularity with this algebraic formulation in terms of matrices that we've been talking about. That's what this next theorem does. The matrix perpendicularity theorem tells us that for any 2 points A and B, A is perpendicular to B precisely when the trace of MA, MB equals 0. So there's one 2 by 2 matrix, there's another 2 by 2 matrix. We're multiplying those 2 by 2 matrices and then taking the trace, which is the sum of the diagonal elements. Now in more advanced linear algebra, or in analysis also, this particular construction is very common kind of thing. Okay? It's a very important general idea. You have 2 matrices, you want to measure somehow how far apart they are, take the trace of the product. That's the first good thing to do. Alright, let's prove this. We'll introduce coordinates for A, say x, y, and z, and coordinates for B, say u, v, and w, and we'll just make the calculation. So the trace of MA, MB is what? Well, it's the trace of this matrix, that's M sub A, and that's M sub B. Alright, so there's the trace of the product. Now let's find the product of those 2 matrices. We're going to take the trace in a second, so it's really only the elements on the diagonal that we need to compute. So this top left-hand corner of this product is y times v plus x plus z times u minus w. Remember, that's how we multiply a row vector by a column vector. And the bottom right component down here is obtained by taking this vector and multiplying it by this one. So x minus z times u plus w plus y v, because the 2 minus signs cancel. And the trace of that is, well, you add them up, and what are you going to get? You're going to get 2 times yv, then xu appears there and also there, so we're going to get 2 of those. Zw occurs with a minus sign there and also with a minus sign there, so we're going to get those. And then the other terms disappear. So the x minus w there cancels with the xw there, and the zu there cancels with the minus zu. So that's all that we end up getting. We can factor the 2 out, and we get 2 times xu plus yv minus zw. So what can we say now? We can say that the trace of this product is equal to 0 precisely when this quantity is 0. And we recognize that's exactly the algebraic form for the 2 points to be perpendicular. Exactly when this point and this point are perpendicular. So an important remark here, because these are projective matrices, the actual trace of the product is not really well defined. It's only defined up to a scalar, because the matrices themselves are projective quantities only defined up to a scalar. But the idea that the trace is 0, that is independent of scaling. In other words, if the trace is 0 and you scale the 2 matrices, well, then the trace is still 0. And if the trace is non-zero and you scale the matrices, the trace is still non-zero. So when we're working with projective matrices, we can't really talk about the trace, but we can talk about whether the trace is 0 or non-zero. That's what we're doing here. We're saying that if the trace is 0, then the 2 points are perpendicular, and conversely. So here's perhaps the main fact about reflections. The reflection preserves perpendicularity theorem. Or we might just say the reflection perpendicularity theorem. If B and C are any points and A is non-null, then B is perpendicular to C precisely when the reflection of B in A is perpendicular to the reflection of C in A. So let's prove it. So A is non-null, and so we know that the matrix M sub A squared is the identity matrix. We need to know a fact about the trace of a product of two matrices, an important fact from linear algebra. And that is that the trace of the product of two matrices A, B is the same as the trace of the product B times A. In general, matrix multiplication is not commutative. If you change the order, the product does change. But the trace of the product doesn't change. Neither, by the way, does the determinant. So, but the trace does not change. That's a little calculation that if you haven't done that before, please check that. Just for 2 by 2 matrices, make some general matrices, calculate both of these, and check that that's the case. So we're going to use that basic fact. So suppose that B is perpendicular to C. We've just learned that that's equivalent to the trace of MB times MC equals 0. That's the same as the trace of MB MC times MA squared equals 0, because MA squared, as we've noted, is the identity matrix and has no effect on this product. And that's equivalent to the trace of MA, MB, MC, MA equals 0. Why is that? Well, because I'm taking one of these M sub A's and I'm bringing it to the left-hand side. Why can I do that? Well, I think of this product as being that matrix times that combination. And if I take those two blocks and switch them around, then the MA comes to the other side. And because of this fact, the trace is 0 still. And now we could manipulate this just a little bit more by introducing an M sub A and an M sub A, which is the identity, right in there, in between the M sub B and the M sub C. Once we've done that, we see that now this triple and this triple here are the M's for B sigma A, the reflection of B in A, and C sigma A, the reflection of C in A. So B is perpendicular to C precisely when the trace of this product is 0, and that happens precisely when this point is perpendicular to this point. So this is equivalent to this. So it means if you have any 2 points, B and C, and you reflect in some third non-null point A, the new points that you're getting are also perpendicular if the first 2 are. Basic fact of reflections. And now I can give another proof of a result that I gave a kind of quick proof for earlier. An important result. Let's call it the reflection preserves lines theorem. It is that if A is a non-null point, then 3 points B, C, and D are collinear precisely when the reflections in A are collinear. If you have 3 collinear points and you reflect in some point A, then those 3 points are also collinear. So we're going to use the fact that we know that reflection preserves perpendicularity. That's the key. So if B, C, and D are collinear, well, they lie on a line L, so that they are all perpendicular to the dual of L. Because the dual of a line is perpendicular to all the points on that line. So little l is the dual of the line through B, C, and D. So suppose that B prime, C prime, and D prime are the reflections of B, C, and D. Well, then they are all perpendicular to the reflection of L. Because we've just learned that reflection maintains perpendicularity. So if B, C, and D are all perpendicular to L, then B prime, C prime, D prime are all perpendicular to L prime. But that means that they all lie on the dual of L prime. So they're all collinear. Here's a picture. Point A, which is non-null. B, C, and D, which are all on a line. The line is the line capital L. And there's the dual of that line, little l. Now suppose we reflect everything in A. The reflection of B in A is this point B prime. The reflection of C in A is this point C prime. The reflection of D in this point is D prime there. And the reflection of the point L is this point L prime over here. So the argument is that if L is perpendicular to B and C and D, then when we reflect all of those, L prime will be still perpendicular to B prime, C prime, and D prime, which means that these 3 points necessarily lie on a line, namely the dual of little l prime. So lines are sent to lines under reflection in A. Lines are sent to line. Any line is sent to another line. And to sort of separate the action of reflection from points and lines, we'll agree to write this relation this way. We'll write L prime equals sigma AL, the line to the right of the sigma symbol, signifying to us that we're talking about lines being reflected rather than points. So here's an exercise for you. Here are 3 points, B, C, and D. Check first of all that they're collinear, and then take the point A and calculate the reflections of B, C, and D in the point A, and check that they also indeed are collinear. You can graph them and repeat with a different center of reflection. Our next concept is the concept of the midpoint between 2 points. If B and C are 2 points, we want to understand this notion of what it means for a point A, say, to be a midpoint of the side BC. We're thinking of something that's like halfway in between in some sense. Well, the some sense in this case is that if we reflect in that middle point, then this point B gets sent to this point C, and conversely this point C gets sent to this point B. So that's our definition. The point A is a midpoint of the side BC, precisely when the reflection of B in A is C. And we better specify that the point A is actually non-null, so that this is symmetric, so that it's equivalent to saying that the reflection of C in A is B. Because remember, we saw that if A is a null point, then the reflection is not necessarily invertible. It collapses everything to the point A. Here's an example. There's a point A, there's a point B. You can calculate there's the reflection C of B in A. And so necessarily this point A is the midpoint of the side BC. Let me remind you that BC, with a bar over it, it means the side BC, and that is just a set. It's just a set consisting of that point together with that point. Now what's maybe a little bit surprising in this hyperbolic setting is that midpoints, first of all, they don't always exist, but secondly, they are not unique. If a midpoint exists, then there will be generally another midpoint too. In this case, this point D, which I've pulled out of a hat, minus 14 to 95 to 149, also has the property that if you reflect B in D, you get C. This is a second point that reflects B and C. And in the sort of picture, you can kind of think of it as being outside somewhere. So we have 2 points A and D, which are both midpoints of the side BC. You can check that that's true. Now we're going to see that to calculate the midpoint of 2 given points is a little bit subtle. It requires solving a quadratic equation. The quadratic equations are always a little bit subtle. I'm going to start by trying to get you to understand geometrically what the midpoints are and how we construct them. Okay? We'll worry about the algebraic approach to midpoints a little bit later on. So I want to show you now that if you're given 2 points B and C, how do you go about trying to find midpoints of that side? Well, there are different cases, okay, depending on the relative positions of B and C. So in this example, the first one, suppose that B and C are both inside the circle. So there's B, there's C. We want to find a midpoint, or maybe midpoints, of BC. Well, here's where they are. There's one midpoint A, there's another midpoint D. How do we construct those geometrically? The first thing that we do is we join B and C, and we find the dual point of that line. So there's BC perp. Then we join B and C to this dual point. So we draw these lines through B and C, and the dual of the line joining them. Now, geometrically in this case, these lines will meet the null circle in 4 null points: alpha, beta, gamma, and delta. So now we have 4 points on the null circle, nil quadrangle, and that's a happy situation. We like these nil quadrangles. We know that we should calculate diagonals of them. So how do we do that? Well, we just join those 4 points with lines in the other possible ways. So we can also join these 2 points and these 2 points. They will meet at some point A. And we can join these 2 and these 2. They will meet at some point D. And these points, A and D, are the midpoints. That's how we construct the midpoints of B and C. And let me show you how to check that. Okay, how can we see that that's actually true? Let's have a look at the reflection in D. How do we calculate that the reflection in D actually does send C to B and B to C? Well, what do we know about this reflection in D? We know that it sends this null point to this null point because these are collinear. That's on the null circle, that's on the null circle. So this reflection in here interchanges those 2 points, and it also interchanges those 2 points. So now the point C lies on this line, so its image must lie somewhere on this line. But it also must lie on the line joining C and D, because we're talking about reflection in D, and so the only possibility is for it to be sent to there. And exactly the same argument holds for the point A. Let's just go through that. Reflection in the point A sends this point to this one to this one. So it also sends this line to this line. And that means that the point C, say, when we reflected A, must lie somewhere on this line here. And it must also lie on this line, and so it must be this point. So both the reflection in D and in A send B to C and C to B. And what makes this work is that these lines that we started by joining BC perp to the original points B and C were interior lines, that they actually did meet the null circle in 4 points. That's an assumption that's valid in this sort of geometrical situation, but it may not always be valid. So here's a variant on that construction. We'll call it construction 1B. Our points B and C are right here. They're on a line which this time is outside the circle. This is an exterior line. We want to find midpoints of this side BC. Well, the dual of this line is this point in here. There's BC perp. And we can do exactly what we did before. We can join this point to C and to B. And then we've got 4 null points being formed. So we have another nil quadrangle. And we can form the diagonals of that nil quadrangle just like we did before. So we find the other 2 intersections of opposite sides. So this one here and this one here, formed by these 4 points, give us one midpoint A. And the other 2, this one here and this one here, well, they're going to meet somewhere up there. we can't expect everything to always be in the diagram that we're making. Sometimes points are off our diagram. But this line, and this line are all going to meet, and where they do meet, that's going to be the second midpoint D. So it's really exactly the same prescription as in the previous case, but the picture's a little bit different because B and C are outside. Let me make a connection with a previous theorem that we talked about, the harmonic quadrangle theorem. When we were talking about harmonic conjugates, we were very interested in quadrangles. And if you look at these 4 points that we have on this line here, the original points B and C, and now these midpoints A and D, we see that A and D are in fact harmonic conjugates with respect to B and C. Right, because in this quadrangle there is one diagonal point, there's another diagonal point, these are both diagonal points, and the line that they form is met by the other 2 diagonal lines of this quadrangle in these points B and C. So in this kind of situation, A and D are harmonic conjugates of B and C. That was discussed in the second video in the series. That construction doesn't always work. Here's an example where we have C and B. There's the line through B and C. But if we take the dual of this line, which is over here, and we join the dual with B and C, those 2 lines don't meet the null circle. So there's no way of getting a nil quadrangle from those 2 lines. The construction is not going to work. Here we can do something different. So this is a construction 2. In this case, what we can do is we can construct the duals of B and C, the dual lines. So there's the dual line B perp. There's the dual line C perp, the dual of that point and the dual of that point. Now those 2 lines will meet in BC perp. And in this case, because B and C are outside, the dual lines meet the null circle here in alpha, beta, gamma, delta. At least they do geometrically. So now we have a new or different kind of quadrangle of 4 null points. And we can use that quadrangle to construct midpoints just like we did the previous quadrangle by finding diagonal points of that. So one diagonal point formed by these opposite lines we've already got. The other diagonal points, one there and one up there, giving us a new point A and a new point D. And you can check exactly the same kind of argument that I was discussing in the last slide, that A and D will also be midpoints of B and C. Not all sides have midpoints. If B is inside and C is outside, then there's not going to be any point that reflects B to C. So this side is an example of something that doesn't have a midpoint. And when we come around to discussing the algebraic aspects of midpoints, we'll see that there's a quadratic equation which determines whether the midpoints exist or not. And that's why when midpoints do exist, there are typically 2 of them, or there are 0 of them. Those are the usual 2 options when you have a quadratic equation. Of course, sometimes the 2 points in general, the 2 solutions of a quadratic equation can coalesce, but typically it's 2 or 0. Now there's a dual notion to the notion of a midpoint. Remember, duality is one of our main principles here. Points are dual to lines. A side, which is a pair of points, is dual to a vertex, which is a pair of lines. And similarly, there's a duality between this notion of midpoint that we've just defined, midpoints of a side, and a dual notion of bisectors of a vertex. These are geometrically playing the role of what you often call angle bisectors in Euclidean geometry. Here's the official definition. We'll say that a line A is a bisector of the vertex BC, precisely when the dual, little a, is a midpoint of the side little b, little c, the dual of these two lines. So we can define bisectors by duality once we understand the midpoint business. This is a rather major difference between Euclidean geometry and hyperbolic geometry. There's a complete duality between the idea of midpoint of a side and the idea of a bisector of a vertex in hyperbolic geometry. In Euclidean geometry, midpoints and angle bisectors behave quite differently. What we're going to do is we're going to focus on the midpoint side of things and develop that a little bit. And then later on, once we understand that quite well, we'll come back to this bisector story, which is in complete duality to it. But I don't want to get things mixed up for you right now. So next time we are going to carry on with more consequences of having midpoints. In particular, we're going to discuss medians of triangles, midlines of sides, circumcenters, and centroids. So some rich triangle geometry is going to start coming into view for us. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.